Okay, so today we're going to be practicing chain rule. Okay, chain rule is the derivative rule when you have a function inside of a function and you split it up into two different functions, one in terms of the other using composites, and then taking the derivative of each one and then multiplying back to get the derivative. So here we have the exponential with tangent plugged in. Okay, so I see a function, the tangent function, inside of the exponential. So chain rule says that I use my inside function as my u, so u is tangent x, and then we rewrite our function in terms of u, so this would be e to the u, because u is tangent x. So then we take the derivative with respect to our variable, so dy over du equals e to the u, because the derivative e to the u is e to the u, and du over dx, the derivative of tangent x, is secant squared x. Then we take these two things and we multiply them to get our dy, our derivative dy over dx, which is going to be e to the u, secant squared x. But we cannot leave it with u inside, so we plug u back in, so this tangent gets plugged back in. So our derivative is going to be secant squared x times e to the tangent x. And that is our derivative. So basically we're taking one function, a composite, and splitting it up into its composite pieces, and then taking the derivative of each one and multiplying them back at the end. Okay? All right. Next, find the derivative of sine squared x. Okay? Now this is a special case because it doesn't look like it is a composite function. But the first thing you should always do whenever you're dealing with a trig function to a power and you're taking the derivative is to rewrite it with the power on the outside. So basically this can be rewritten as y equals sine x squared, like that. Now, you could also, if you wanted to, rewrite this as y equals sine x times sine x, and you could do product rule there if you wanted to. But since we're trying to focus on the chain rule, we're going to do it chain rule style. Okay? Now, neither of them would be incorrect, whichever path you chose, but since we're practicing chain rule, we'll do a chain rule. Okay? So again, we pick our u, which is our inside function. So u is sine x. And then we rewrite it as y equals u squared. So you can see here that now I have two super simple derivatives. So dy over du is 2u, and du over dx is cosine x. And then again, we multiply these two things and we have to plug our u back in, which is sine x, and we get y prime is equal to 2 sine x cosine x. And that's our derivative. Okay. All right. Next, we have this function, and we have quotient rule going on here. Okay. So we're going to start. Our main idea here is quotient rule. Now, in the one previous, the main driving derivative was chain rule. But this one, the main driving rule is quotient rule because of this division. We have a function divided by a function. Okay, so we start with quotient rule. So it's the low function, x squared minus x, times the derivative of high. Now, as soon as I go to take the derivative of tangent squared, you can see that all of a sudden it looks like the problem we just finished which means we're going to have to do chain rule to find that. So I'm going to come over here, and just like I did on the last one, move the power to the outside, like that. Okay, so I'm separately, notice that I'm doing this separate from my other derivative. So over here, I'm going to put whatever I find right there. But I'm doing this separate so that I can focus just on doing this tangent squared. Okay, so u is my tangent x, and y equals u squared. So it's very similar to the last one. So you get dy over du equals 2u, and du over dx is secant squared x. Plug back in and multiply them. So the derivative, you take the derivative of this, equals 2 tangent x secant squared x. And that's what I'm going to put right here. 2 tangent x secant squared x. That is all just the derivative of tangent squared. Okay? Minus, now we're going to finish our quotient rule. Now we take the derivative, the derivative of the bottom, which is 2x minus 1 times the top, which is tangent squared x, all over the bottom one squared, which would be x squared minus x squared. And that's our derivative. Now, it didn't say to simplify, so we're not going to simplify it. We found our derivative, f prime of x, okay, and we are done. Okay, all right. Now the last one. Okay, so just like we've been practicing, and I've talked about in my other videos, sometimes or very often what we're supposed to do is rewrite. Okay, so this one you can see very quickly we need to rewrite this one, especially as soon as you see that root power. Okay, so let's rewrite d over dx, and this root power is going to be the 1/3 power, and then we're going to move it to the top. So it's going to be the negative 1/3 power. So basically we get e to the x, and it's going to be to the negative 1/3 power. So that's what we're going to be taking the derivative of. And you can see now we have this function inside of that function. So to make it easier, we're going to do chain rule. So my u this time is e to the x, and then when I rewrite it, I get u to the negative 1/3 power. This one's the easy one. Du over dx is e to the x. Dy over du is going to be, now we do just power rule, so negative 1/3 u, and when we subtract 1 from negative 1/3, we're going to get negative 4/3. And again, we're going to multiply this, and then we're going to put our u back in here. But before I do that, I'm going to deal with this power. So I get negative 1 over 3 times the cubed root of u to the 4th times e to the x. And then when you simplify it, the e to the x is going to go to the top. So you're going to get negative e to the x over 3, and this is the cubed root of e to the x to the 4th power, which you could simplify it even further to negative e to the x over 3, and this would be the cube root of e to the 4x. Because when you take a power to a power, you multiply them, and so you would get this.